In this lesson, we're going to talk about signed number systems in terms of binary numbers. First, we'll take a quick overview of unsigned binary numbers that we spoke about in a previous lesson, and then we'll talk about how to turn these into signed numbers. Right, we'll talk about how the decimal number system does it, and then how we're going to do it in binary using Radix and Diminished Radix complements. And we'll see that there's three schemes for doing this in binary. There's a signed magnitude scheme, a ones complement, which is a diminished Radix complement, and a twos complement, which is the Radix complement. Right, and then we'll also talk about the range of numbers that we can represent with the different schemes, and then we'll give a list at the end, student to-do list of things that you should study, concepts, important concepts from this lesson. All right, so let's go back and briefly talk about unsigned binary numbers. Right. Remember, the binary number system, it's a base 2 system, so we only have two different numerals to represent quantity. We have 0 and 1. Right. We can use several binary digits or bits to represent different numbers. So any number that has m binary digits, right, can represent 2 to the m power unique patterns. Right. We'll see that when we work with signed numbers and we use the same number of digits or bits, we still only have the same number of patterns to work with, and we'll have to interpret the meaning of those patterns differently. Right. Let's look at an example then of if we had m binary digits. Let's let m be equal to 4. Right? If we have 4 bits, binary digits, then we could represent 16 unique patterns. Right? So let's take a look at that particular example. All right, so I've got a little spreadsheet table going here, and I've got the 4-bit positions here. So remember, we talked about positional notation of any number. The least significant bit will be 2 to the 0 power. The next will be 2 to the first. Next will be 2 squared, and then 2 cubed. All right, so we said with m equal 4, so m equal 4, right, we can have 16 unique patterns. And those unique patterns look something like this, right? 0, 1. We start counting here. Actually, let me fill this in line by line. If we start counting 0, 0, 0, 0, here's our first pattern. So we start with all zeros, right? And if we give this meaning in the base 10 number system, right, if we translate this, this is the number 0. We then represent the number 1 as 0, 0, 0, 1. Here's our next binary pattern. So I'm going to count out by 1. Right, I'm going to be adding 1 every time to this. Right, so the next number, our next unique binary pattern is 0, 0, 1, 0, and that represents the number 2 in decimal. We want to represent the number 3. Here's 3, right, and so on. We can keep filling this in. Here's 4, right. 5 is 0, 1, 0, 0, 1. Remember from your last lesson? Right. You were told that it's very important to start learning these patterns. Hopefully you've worked on that and you're starting to recognize these as well. And what you should be doing right now is go ahead and be writing these down on pencil and paper so you can practice this pattern. All right, there's 8. So 8 is 1 times 2 to the 3rd. Add 1 to that to get 9. And then 10 becomes 1, 0, 1, 1, 0. 11, we add 1 to that. 11 is 8 plus 3. 12 is 8 plus 4. 13 is 8 plus 4 plus 1. 14 is 8 plus 4 plus 2. And 15 is 8 plus 4 plus 2 plus 1. Right. So with 4 bits, m equals 4, we have these 16 unique patterns, and they equate, for unsigned numbers, they equate to the decimal values 0 through 15. Right? So there's an example of how we represent our unsigned values. We go back to our slideshow here. All right, so m is the number of bits we have. We can see in this most simple example, if we have 1 bit, right, we can represent 2 to the 1, 2 unique binary numbers. And those numbers are 0 and 1. Right? As we build, right, we just saw that if we have 2 binary digits, right, we can represent 2 squared, or 4 unique binary numbers. So here's the pattern, 0, 0, 0, 1, 1, 0, 1, 1. So those are the 4 unique patterns we can represent. So remember, m is the number of bits. Here with m equals 3 binary digits, we can represent 8 unique patterns. So here's our 3 bits, our powers, and here are 8 unique patterns. All right, so let's take a look then at this table. If we have 3 binary digits, we said we have 8 unique patterns, and if we want to equate those patterns to unsigned decimal, right, base 10, so here's the value, the magnitude. Remember, this is all unsigned. We have the numbers 0 through 7, or these 8 unique numbers, right? Now let's talk about how we might represent signed numbers. Right? Those were all unsigned. They just had a value, an absolute value to them. Right. We know that in base 10 number systems, numbers can be positive or negative, and negative numbers indicate a place in a coordinate system. We can't translate negative numbers to the real world in terms of having negative physical objects, at least in the physical world. But in the math world, in our coordinate system, we can have negative numbers. They indicate a relative position. Now in base 10, we know that with negative numbers, we just simply precede them with a minus sign, right? If I have minus 34, I know that that's negative 34. So anytime I need to indicate a number's negative, all I do is place the minus sign in front of it. Positive decimal numbers are preceded with a plus sign. So here's an example, plus 3, plus 19. When there's no sign, we always assume that a number is positive or unsigned, right? Plus 3 is the same as if we just write 3. We assume that that is a positive value, right? Plus 19 is the same as writing 19. We assume that's a positive value as well. But we always use the negative sign to indicate a negative number. When the sign is absent, right, we assume the number is positive, or we can place a positive sign in front of a number. Right. Now, to do that in other bases, we don't have a positive or a plus or a minus sign. Right? Especially in binary, all we have in binary, remember, are zeros and ones. So we're going to have to come up with a scheme to represent a negative number. Right? Sorry about that. All right. But what we're going to do is we're going to take one of the bits, right, in our system, and we're going to treat it as the sign bit. Right. So there's 3 widely used techniques for representing signed binary numbers. First, we'll take a look at the sign magnitude form, and then we'll look at the complement forms, the ones complement and the twos complement forms. Let's go back then to our m equals 3 bits. Remember, we said we have 8 unique patterns, and we came up with these 8 unique patterns for 3 bits. Now, we said if this was an unsigned number, remember we said that this would represent 0, 1, 2, 3, 4, 5, 6, and 7. Now, if we write these same patterns and we want to treat these as signed numbers, right, we still only have the 8 unique patterns, but we're going to have to take one of the bits and use it to indicate the sign. So we're going to have less numbers to represent the magnitude. Right? So if we take that table that we just had, and now we say we take the most significant bit, and we treat that as a sign bit. So we'll do that in all of these schemes. Our most significant, our leftmost bit, will be the sign bit. So now we've removed this one bit here. We're left with just 2 to the m minus 1, in this case 2 squared unique patterns. Because we split this table in half, let's look at this. If I say this is the positive half, well, I have 0, 0, 0, 1, 1, 0, 1, 1 here. Right. In the negative half, notice I have the same scheme, 0, 0, 0, 1, 1, 0, 1, 1. So I only have now 4 unique patterns to represent magnitude or value. This bit will represent a sign. If I treat this half as being positive, right, and this half as being negative, we'll see then how we do that with sign magnitude and what those numbers represent. All right. So let me remind you that the magnitude of any number is usually called its absolute value or modulus. And we denote that mathematically with the 2 vertical bars on either side of x. So this says the absolute value of x is equal to x if x is greater than or equal to 0. The absolute value of x is equal to negative x if x is less than 0. Right? And here's a couple of examples. The absolute value of 3 is 3. The absolute value of negative 3 is the negative of the negative of 3, right? That complements that out and gives us the value 3. So that is the number's magnitude, right? The magnitude of minus 3 is 3. The magnitude of 3 is 3. So next we'll take a look at the sign magnitude form. In sign magnitude form, it's the easiest to understand because we're going to do what I just said. We're going to take the most significant bit and treat it as a sign bit. And what we need to know then is that 0 represents positive. So in the sign bit position, when you see a 0, that will mean a positive number. When you see a 1, that will mean a negative number. We'll use the remaining bits to represent the number's magnitude or absolute value. So let's go back to our binary number m that has 3 bits. We're going to take the most significant bit, the leftmost bit. So actually, that should be, let me correct that typo. This should be, let's see this. All right. Sorry, I had a typo here. This should be 2 squared. All right. So once again, we have m equals 3 bits. The most significant bit, this leftmost bit, will be reserved as a sign bit, and we'll just have these 2 bits to represent the magnitude. All right. So that only leaves us with 2 bits to represent the number's magnitude. 2 squared is 4, so we're only going to be able to represent 4 unique magnitudes with those bits. So if we start filling in the chart, we fill this in with our pattern of 0, 0, 0, 1, 1, 0, and 1, 1. Those are our magnitude bits, right? Those are the 4 unique numbers. And equivalent decimal magnitude, right, of these numbers, this would be 0, this would be 1, this would be 2, and this would be 3. We're going to go ahead then, sign magnitude, and fill in a sign bit here. So when we fill in the sign bit 0, remember we said 0 is positive. So all of these become positive in this half because I'm going to maintain that same unique binary pattern, right? That unique binary pattern that we saw before for the 3 bits was 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. We have to, each representation has to be unique. This is known as positive 0. This is positive 1, positive 2, positive 3. Because with sign magnitude, the way this works is we say if we want to know what the value is, we look at the magnitude bits. The magnitude bit here represent the number 0. Then we look at the sign bit and say that's positive. So this represents, in sign magnitude formation, plus 0 or positive 0. This represents plus 1 because we look at the magnitude of the number of these 2 bits. We say this is a 1. The sign bit means this is positive, so this is positive 1. Same way here, we look at the magnitude of these 2 bits, 1, 0. We say that's 2. We look at the sign and say this represents plus 2. And finally, here, we know this represents 3. Look at the sign, and we say this is plus 3. So this is the equivalent base 10 representation when we use sign magnitude form. Right. Now, we still have 4 empty rows in our table. We need to maintain that same unique binary pattern. So in this bottom half of the table, we're going to fill in 1s as a sign bit. So we'll fill this, this, and this with 1s. So we filled this with 1s. Notice we repeat the same pattern as in the upper half of the table with these 4 bits. And now if we want to know their value, we look once again at the magnitude. The magnitude of these 2 bits is 0. Then we look at the sign and we say -0. We're not used to representing -0. We always just say 0. We don't say +0. We don't say -0 in a base 10 system. But with this particular system, sign magnitude, we actually end up with 2 representations of 0. We end up with a +0 and a -0. It's not the best solution. We'll end up seeing that 2's complement is a better solution for our hardware, but this is the easiest one to understand at this point in terms of, well, let's take the magnitude just like we do in base 10 and let's put a plus or a minus sign in front of it. We're used to that. Okay, let's see where we came up with these other numbers. Once again, the magnitude bits are these 2 bits here. This is a 1. We look at the sign bit, and we say this is negative, so we get -1. Here we look at these 2 magnitude bits. This is a 2. We look at the sign bit, negative. Right, so -2. And finally, this is -3. Right. So now, with sign magnitude, with 8 bits, we can represent the numbers +0 through +3 and -0 through -3. Right, notice this looks like the same pattern as unsigned binary. So when you're given binary numbers, you have to be told whether they're signed or unsigned, and then what scheme was used to form them, right, in order for us to interpret meaning from these patterns. All right. So now if we want to form some sign magnitude numbers, let's go back to our 4-bit example. Right? Now we're going to have 4 bits to work with. We saw with our other example, with 4 bits, we could represent 16 unique binary patterns. Right. We're going to reserve then, out of these 4 bits, we're going to reserve the leftmost bit as the sign bit. So that now leaves us with 3 bits to represent the number's magnitude. Let's go back to our spreadsheet and I'm going to clear these contents. All right, we're going to change this to 4-bit signed magnitude. All right, so this is the same unique binary pattern here and here that we had formed with 4 bits. But now we want to remember that this becomes the sign bit here. So let me indicate that this is now the sign bit. All right, so we keep this unique pattern. We say, well, how are we going to interpret this now? All right, well, we look at the numbers magnitude here. Here are the magnitude bits. And the magnitude bits here of these 3 bits are the number 0. We look at the sign bit and say a 0 is positive, so this becomes +0. We now look at this and say, what is the magnitude? Well, the magnitude's 1. What's the sign bit? Plus. So we say this is +1. And let me correct this. My sign bit disappeared up here. So +1. Same way here, we look at this. We say, well, what's the magnitude of these 3 bits? Magnitude's 2. What's the sign? Plus 2. All right? And this is how we fill in this table. All right, the next one, the magnitude will be 3. Look at the sign bit, plus 3. And we get plus 4. And we get plus 5. And then we get plus 6. And finally, plus 7. All right, that takes care of the top half of the table for the magnitude. Now notice here, the magnitude starts to repeat. We have a magnitude of 0, 1, 2, 3, 4, 5, 6, 7. But the sign bit is different. So we look at this and we say, well, this number is in sign magnitude form. So the magnitude of this number is 0, but what's the sign? The sign is negative. So we say this number is negative 0. Oh, signs is negative 0. And then we have negative 1. Right, and then we have negative 2. We have negative 3. Negative 4. Negative 5. Negative 6. And negative 7. All right. Once again, all we did was we looked at the magnitude of this. We said the magnitude is 1. What is the sign? The sign bit is a 1, which is negative, so this must be a negative 1. That's how we do this in sign magnitude form, which is what these slides then begin to represent, right? Here's our magnitude, our base 10 magnitude of 0 through 7. Here are our magnitude bits. We took this leftmost bit as the sign bit. We're going to fill in zeros, right? So this is the table we just formed. Here, we filled in all these zeros. Here's our here's our decimal value over on the right. And then here's the remainder of the unique binary pattern where we have all of the sign bits are 1s, right? And here are our decimal representations of -0 through -7. Right. Now we've noted the fact that we have a special case here, right? We've got a -0 and a +0. That can cause complications for a computer when they're checking numbers for equality, right? Because one thing computers do all the time is they compare values, right? Mathematically, we compare values quite a bit. And it can be very confusing then if we have, scroll wheel got me, right? If we have separate representations for 0, because -0 and +0 are the same thing. 0 is just 0. So that special case can cause us to either create more hardware or different software interpretations, and it's inefficient. So this was one of the first forms that was proposed to keep track of signed numbers in digital computer systems. Then another system that was proposed is what's called the sign complement system. But let's go ahead and look at another example before we talk about sign complement. So here's an example where we can convert a binary sign magnitude number to decimal. So we're told if we're given this number here, this number right here, 11001, it's a base 2, and we're told that this is a sign magnitude number. We're told how this number was formed. So we interpret this number by converting all the bits to the right of the sign bit. So remember, this is the leftmost bit is the sign bit. The 1 here is the sign bit. The 1001 is going to be our magnitude. So if I write this down below in this table, right, I separated out, here's the magnitude bits, here's the sign bit. So if I was writing this on a sheet of paper, right, write this number down, circle these magnitude bits, and then convert the magnitude bits to their magnitude. So this is 9, and then look at the sign bit here, and we say, oh, a sign of 1 means it's a negative number. So this value must be -9. And that's how you do an example conversion. Here's another example conversion. We're going to convert this number, which we're told is in sign magnitude form. We want to convert it to base 10 to decimal. So once again, we convert all the bits to the right of the sign bit to their equivalent decimal magnitude. So we have these 4 bits to the right of the sign bit. Remember, the leftmost bit, this is the sign bit. And I apologize, I have another typo here. Copy paste I copy paste sometimes, and that gets me into trouble. So I just changed this. Our sign bit 0 goes here. Here's our magnitude. Notice the magnitude is the same in the previous example. It's a 9. The sign bit is different. So this is the plus 9. So this is sign magnitude for plus 9. Pretty easy to convert, right? We just remember that the signs represent positive or negative, convert the magnitude. All right, that's it for sign magnitude form. We're going to start talking about what's known as the diminished radix complement. In binary, that is known as the ones complement. The complements are used in digital computers to simplify a subtraction operation. Right? If you think about it, if we wanted to perform a minus b, algebraically, we know that this is the same as a plus negative b. When we represent numbers in their negative form, we don't have to make separate hardware, right? If we needed to make hardware to perform addition, a plus b, and separate hardware to perform addition, a minus b, it takes up real estate on our chip. In other words, on a computer chip, integrated circuit, we use more transistors to create separate circuits. Well, that complicates our design, and we'll see eventually we're going to learn to make adders in this class, that if we create a circuit that can either add positive or negative numbers together, we have less hardware that we use and we have more efficient operations. Right? So in our digital logic systems, we will implement subtraction as a plus the negative number. Now we're going to see that there's two types of complements that we can use for each base R system. The radix complement, where R is the radix, and the diminished radix complement. So we refer to the radix complement as the R's complement. So remember, in a base 2 system, R is 2, we'll have the 2's complement. The diminished radix complement is the R minus 1's complement. So in a base 2 system, 2 minus 1 is 1. We'll refer to this as the 1's complement. All right, so our diminished radix complement, this is what I just stated. We'll call this the ones complement. So for binary numbers, the diminished radix is 2 to the minus 1 equals 1. It's called the ones complement. We'll see that when actually we interpret a number, so given a number n in base R, so given some number in base R, and that number has n, small n digits, right? The R minus 1's complement of n, otherwise known as its diminished radix complement, is defined as R to the n, so the base raised to the number of digits minus 1, then minus the original number n. All right, we'll see how to do this in binary. It's very simple, the ones complement. All right, so when we substitute in the value of 2 for the radix, we're going to see that if we want to take a number n and find its ones complement, we'll have to compute 2 to the n minus 1 minus n. That seems like a lot of math. We're going to observe that there's a really simple way to do this in binary. So let's take a look at that simple way. All right. So let's calculate a ones complement number. So the first thing we do is we find the binary representation of the number 2 to the n minus 1. Right? We represent the number n in its unsigned binary form, and then the ones complement of n is 2 to the n minus 1 minus capital N. All right, so let's take a look at a 1-bit number. That's the most simple number we can have. So we're going to say that our number n here is 0, and it has little n 1 bit, right, 1 bit. So here, 2 to the n minus 1, well, this is 2 to the 1, because n is the number of bits. 2 to the 1 is 2. If I subtract out 1, that gives me the number 1. Right. So I found this much of the formula. Right? So I'm trying to find the ones complement of n. N is 0. Here is then the 2 to the n minus 1 calculation. 2 to the little n minus 1 gives us 1. And then to finish this calculation, once I found this step, I take this and I subtract it. So here's the 1 from here to here, 2 to the n minus 1. We're going to subtract out n. N was 0. 1 minus 0 equals 1. In other words, the ones complement of n, when n is 0, is 1. Okay, that was a lot of math just to get from here to here, right? But bear with me. Now let's look at the other possibility for n. So when we have a 1-bit binary number, the other value n could take on is the number 1. Once again, this calculation is the same. It's 2 raised to the number of bits. Well, there's only 1 bit, so 2 minus 1 gives me the number 1. So now when I complete this calculation, right, of this form, 2 to the n minus 1 minus n, right, I take 1, that's this one here, 2 to the n minus 1, minus n's value. N's value is 1, so 1 minus 1 equals 0. And I find that the 1's complement, the binary 1's complement of 1 is 0. So we found that the binary 1's complement of 0 is 1. The complement of 1 is 0, right? And that makes sense because there's only 2 possibilities, right? When you have 1 bit in a binary system, it can only take on the number 0 or 1. So the complement of 0 is 1. The complement of 1 is 0. We'll use this idea for the rest of the semester in terms of complements. All right. And this just sums it up, right? When the bit in the number is 0, the subtraction step yields a result of 1. When the bit in the number n is a 1, the subtraction step yielded a result of 0. So the complement of 1 is 0 and the complement of 0 is 1. Important concepts. We'll actually have a logic gate that forms complements for us. It doesn't need to do all those subtractions. All right, so we'll have a very simple circuit eventually when we learn about those circuits. For right now, remember the complement of 1 is 0, complement of 0 is 1. Right? It's the opposite. All right, now if we go ahead and we look at a 2-bit number, right, a little more complex. Remember, we said to form the 1's complement of any number n, we use this formula where 2 is raised to the number of bits minus 1 minus the number n. So when we have 2 bits, we could have 4 possible values. So 2 raised to the number of bits, 2 squared, gives us 4 unique values. Here are our 4 unique values in the table: 0, 0, 0, 1, 1, 0, 1, 1. Now, when we perform this step, this 2 to the n minus 1 will be the same for all steps. Remember, this is 2 to the n, so where n is 2, right, this is the number 4. 4 minus 1 gives us 3. That's where this 1, 1 comes from. Remember, 1, 1 is a representation of 3. So if we take this here and we subtract out n, so 1, 1 minus 3, minus 0, so 3 minus 0 gives us 3. And we find that the 1's complement of 0, 0 is 1, 1. Which makes sense because didn't we just say that the complement of 0 is 1 and the complement of 1 is 0? So we'll see that we can just simply take each one of these bits individually and complement them. But let's go through the formula to make sure that works out. Right, so now here n is 1. So if we take 3 minus 1, we get the number 2. Well, the binary representation of 2 is 1, 0. Well, this 1 is the complement of this 0. This 0 is the complement of this 1. All right, let's look at this. 3 minus 2 gives us 1. So the 1's complement of 1, 0 is 0, 1. And finally, 3 minus 3 gives us 0. So the 1's complement of 1, 1 is 0, 0. We just took the complement of this 1 is this 0. The complement of this 1 is this 0. Right? The complement of this 1 is this 0. The complement of this 0 is this 1. But we don't really have to perform all these subtractions. We can just simply individually complement these bits. But I wanted to show you mathematically that when we follow the formula, we arrive at this, right? But we don't want to have to follow this formula all the time. We want to just be able to take these individual bits, and whenever we have a 0, we know that the 1's complement of that will be a 1. Right? Whenever we have a 1, the 1's complement of that is a 0. Very easy to form the 1's complement. Right? If we were to go ahead and do this for 3 bits now, right, we end up following the same formula of 2 to the number of bits minus 1 minus n to form the 1's complement. Right? We have 3 bits, so this part of the equation, 2 to the n minus 1, well, that's 2 cubed. minus 1 gives us the number 7 in base 10, which is 111 in binary. So here are 8 unique values of big N. Right? So here are 8 unique values of big N. We know that this part, 2 to the n minus 1, gives us this binary representation of 7. Well, 7 minus 0 gives us 7. Right? So 111. And notice all we did was we complemented each one of these bits. All these zeros became 1s. Here, if we perform the binary subtraction of 7 minus 1, we get 6. So there's the binary representation unsigned. When I give you these values, these are unsigned, 110. Notice this 0 became this 1. This 0 became this 1. This 1 became this 0. Similarly, if we go through this entire chart, we'll see that this 0 becomes 1, this 1 becomes 0, and this 0 becomes 1. So all we do is we take the number and complement the zeros and ones to form the ones complement. We don't have to go through the subtraction step. This shows you that it matches the algebraic formula, but we can more simply, very quickly write down without going through this step what the ones complement is. All right? So we've seen this ones complement pattern, right? When we had 1 bit, we saw that the complement of 0 is 1. The complement of 1 is 0. The complement of 0, 0 is 1, 1. Complement of 0, 1 is 1, 0. And we observed all the way through that everywhere we have a 0, the complement of that is a 1. Everywhere we have a 1, the complement of that is a 0. So it's very easy to form the ones complement. But let's take a look at actually these numbers here. So in this column, we want to know what the ones complement is. Well, the ones complement of this, actually, let me just go ahead and let's fill in this chart together. So I'm going to move these over here, the originals, and I'm going to clear that out. And we want to say, well, what's the ones complement of this? Well, the complement of this leftmost 0 is a 1, 0, 0. Right? And same way here, complement of that leftmost 1 is a 0, and then a 1, 1, 1. And then, yeah, excuse me, the opposite of 1, 0, 1, 0 is 0. Gotta watch my cursor. All right. Complement of that is 0, 1, 0, 1. So here where I had this 1, I replaced it with a 0. Where I had this 0, I replaced it with a 1. Where I had this 1, replaced it with a 0. This 0 replaced with a 1. Same way here, complement of this is 1, 1, 1, 0, 0, 1, 1. So I just started from the left. Complement of this is 1, 1, 1, 0, 0, 1, 1. Complement of 0 is 1. So you can see now that we've observed that pattern, we don't have to go through all that math in order to calculate that. Right. Now, we know how to form a ones complement number. What we're going to talk about next is how do we interpret its value. Right. We've already been given some information. We know about positional notation. Right. We have to know how a number was formed, so we have to be told when we're given a number that it is a signed number and it's in ones complement form. So remember, once again, we're going to treat the leftmost bit as the signed bit. Right. So if we're given a number here, let's look at this chart. In unsigned binary, if we had these 4 unique patterns, we said that, well, 0, 0 represents base 10, 0, 1, 2, and 3, with these 4 unique patterns. Now let's take this same set of patterns that we have here, and we have the same pattern here, but now we're told that these are binary ones complement. So this is very similar to sign magnitude in order for us to determine how to convert it, right? We take a look at this at 0, 0, and we say as long as the sign bit's a 0, we just work from the magnitude. Let me just actually bring this same thing up in a chart here. All right, so we're going to say what is the decimal value of the following. So let me minimize this. Actually, the following ones complement binary numbers, right? Actually, let me just center this back a little bit. Make that bigger. All right. So we're going to say this number is 1's complement. All right. And we have the sign bit and the magnitude bit. And I'm going to write the same pattern All right, so these numbers are in 1's complement form. All right, so let's take a look at this one. We want to know what is the value. Let me move this out here. Our original question. What is the decimal value of the following 1's complement numbers? Right. Actually, sorry that got off the screen there. Okay. We want to know what the value then of this is. Well, how do we interpret that? Once again, if we're told the numbers in 1's complement, we look at the sign bit. When the sign bit is positive, so once again, 0 represents a positive number. So 0 represents a positive Let me make this bigger. Okay, so step 1, we look at the leftmost bit. It is the sign bit. All right, so we look at that, and we say 0 represents a positive number. Right? So step 2, when the sign bit is 0, convert the remaining magnitude bits to decimal. All right. All right. Let me just write this in here. All right. Let me move this down, make this more readable, and then we'll go back through this. All right, so step 1, look at the leftmost bit is the sign bit. So leftmost bit, sign bit here. 0 represents a positive number, 1 represents a negative number in the sign bit position. So we do that, and then in step 2, we say when the sign bit is 0, right, we convert the remaining magnitude bits to decimal. So here, the magnitude of this is 0. Let me put in another column here. This is going to be our decimal value. Let's make the font of that. All right. So we look at the sign bit's positive. So then we look at the magnitude, and we just simply convert, because this is positive, we say this is plus 0. And I got it. All right. And let me center that so you can see that better. All right, so this first one, we said this is plus 0. Right. Whenever you're converting one's complement to decimal for a positive sign bit, this is just the same as sign magnitude, isn't it? Well, that's what we've seen so far. Let's take a look at this one. So here, once again, we've got a 0 in the sign bit. I've got a 1 in the magnitude bit. So I know this is plus 1. Right? Because I followed these steps. I looked at the sign bit. I said 0 represents a positive number. We said here, when the sign bit is 0, right, we convert the remaining magnitude bits to decimal. Right. But now, what happens when it's negative? Right. And it's not quite what I wanted to do. All right. So when the sign bit's 0, we convert the remaining magnitude bits to decimal. Right. When the sign bit is negative, complement the magnitude bits, and then convert the complemented bits to decimal. All right. So what happens then when the sign is negative? We take this bit, 0, so the decimal value of 1, 0 is minus 1. Because there is a negative sign bit of 1. The magnitude bit, 0, is complemented to 1. Giving us negative 1. So this is minus 1. All right. Now let's take the decimal value of 1, 1 is minus 0. Because there is a negative sign bit of 1, we complement the magnitude bit 1 to 0. giving us minus 0. So here, minus 0. Right. Now, you can see with the ones complement scheme, we have the same problem that we did with sign magnitude. We have a plus 0 and a minus 0. So we'll eventually go on to a 2's complement scheme then to get rid of this problem. Let's go back to where we were in the lecture, right? And we were back at this table. So we just developed what was here. We said we had these numbers that were binary ones complement, so we had this pattern here. We wanted to know what the decimal value is. We said in order to do that, we always look at the sign bit. When the sign bit is positive, all we do is take the magnitude of this number and say this is its value. So this, more appropriately, plus 0. This is plus 1, right? Because the sign bit is positive. So we just simply convert the magnitude and have plus 1. We said then, when the sign bit's negative, we know that we have to put in the negative sign, but then we have to complement the magnitude bit, this bit here. So minus 1, same way here, the sign bit is negative. We complement the magnitude bit of 1 to get minus 0. All right, and this goes through what we just went through in the table, but it's written out a little bit more neatly for you to follow. Right? We said given the binary ones complement number 0, 0, we convert it to decimal. So I simply show you here, here's the binary ones complement. I broke it up into the sign bit and the magnitude bit, right? So the sign bit's the leftmost bit. We said when its value is 0, we know it's a positive decimal value. The remaining bits to the right of the sign bit, so there was only one remaining bit, it represents the number's magnitude. So the ones complement decimal value is plus 0 of 0, 0, right? And these remaining slides then go through this as well. We did the same thing. We wrote down the binary ones complement. We said, let's take a look at the sign bit. The sign bit is 0. We know that's a plus sign, so then we just convert the magnitude to decimal. The only time we need to perform the complement here, when going from binary to decimal, is when we have a negative sign. So now we have this binary number. The sign bit in this case is a 1. So we have to then take the remaining bits to the right and we complement them. And then we take the magnitude of this. So here was the 0 in our magnitude bit. The complement of that was a 1, so we end up with a minus 1. And same way here for the 1, 1 case. We said in this case the sign bit is a 1. That tells us to put a negative sign in our answer. We complement the magnitude bit of 1 to 0 and see that our answer is minus 0. Right. And there's a table just summarizing what we did. Right. Now, let's take a look at how we would do this with a 3-bit representation. So let's actually copy paste. See if we can copy paste this into a spreadsheet and come up with how we do this. And formatting doesn't hold here, so 2 to the 1, 2 to the 0-bit position. Right. These are magnitude bits. Let's see how we form the base 10 values. All right, So we take a look at the sine bit. And okay. This is going to be our decimal number. So the sine will go here. And look, everywhere we have a 0, the sign is going to be plus. Everywhere we have a 1, the sign will be negative. So what we do then is we take, all right, remember, when the sign is positive, convert the magnitude bits to decimal, or I'll say to base 10, right? So what are our magnitude bits? So R. All right, for the positive sign, we have 0, 0. Right. I have to put the single quote there in order to keep our format. All right. So here for this first one, right, we've got, here's our magnitude bit, 0, 0. We said our sign was positive, magnitude bit 0, 0. Complemented bits, right, well, we do not complement when the sign is positive. Okay. So we don't form the complement of any of these. And we say then, finally, that our decimal value, right, well, this is going to be plus 0. This is going to be plus 1. This is going to be plus 2. Plus 2, I don't want to lose my sign, plus 3. All right, here's our plus sign. Here's our magnitude. 0 becomes 0. Plus sign, the 0, 1 becomes 1 in base 10. Plus sign, this 1, 0 becomes 2 in base 10. Plus sign, this 1, 1 becomes 3 in base 10. Right? Now for negative bits, we have the same pattern of magnitude bits, don't we? But for negative bits, remember we said then when the sign is negative, complement the magnitude bits and then convert the complemented bits to base 10. And let's make that a little more readable. So when the sign is negative, complement the magnitude bits and then convert the complemented bits to base 10. It's easier for me to do it than to say it. All right, so we take these magnitude bits, So the complement of 0, 0 is 1, 1. The complement of 0, 1 is 1, 0. The complement of 1, 0 is 0, 1. And the complement of this is 0, 0 of 1, 1. So now I look at this and I say, here's my negative sign, right? I know that the number is negative. And then this is a negative 3, right? Because I had to complement the bits, and then I take this magnitude of this. So this is negative 3. So this pattern here is 1's complement for negative 3. This pattern then, right, we know this is a negative from the negative sign. We take the complemented bits and we convert that to base 10. So that is minus 2. Sorry, minus 2. This is minus 1, and this is minus 0. Right, because this is 2, negative 2, negative 1, negative 0. Right? And so we see then that this 1, 1, 1 in 1's complement actually means negative 0. This 1, 1, 0 means negative 1. We need to follow these steps. Whenever we convert from binary to decimal, we always look at the sign bit. Right? And we know from the sign bit then, when the sign bit's 0, in this case the sign bit's 0, we got all these positive signs. Right? When the sign bit was 1, we got all the negative signs. Right? Then we look at the magnitude bits. So the remaining bits here were the magnitude bits. These are where these came from. And we said, well, whenever we have a positive sign, those were not formed with a complement, so we don't complement them back. We just simply convert this magnitude, 0, 1, 2, and 3, here to get these values. We said when we have a negative sign, then we know in order to get these numbers, they were actually complemented. We have to complement them back and then take the magnitude. So you have to do quite a few of these to get into the practice of knowing what they mean and how to form them, how to translate them from one system to another. Right? So you'll be given practice exercises and homework so you can get good at this. Right? Whenever you first start doing this, write down these steps. Right? Either I write down the steps in my homework. As a student, whenever I performed this, as I started doing this, I started writing these steps down to practice until it became second nature to me. I find that when I write things out by hand, it stays in my memory longer. Right? So I would suggest that a good exercise for you now is to copy down the same chart here and then form the same thing we just did. Figure out what the values of these numbers are in base 10. Right? Practice this right now. All right, so that's where that came from. Then these values here, that's where they came from in this table. All right. Same thing, we can express a 4-bit representation. So if we have 4 bits, we have 16 unique patterns. Remember, 2 to the 4th is 16. All right, so we have these 16 unique binary patterns. We can calculate the decimal value of all of these. Notice here the sign bit was 0, so I know that these are all positive, so I can simply take the magnitude. This will be plus 0, plus 1, plus 2, plus 3, plus 4, plus 5, plus 6, plus 7. Right, that's where all of those came from. From this was a negative sign, so I needed to complement this 0, 1, 1, 0. I complement this back to 0, 0, 1 to give me minus 1. This is a negative sign, so I form the complement, which is 0. Complement of this magnitude, 1, 0, 1, is 0, 1, 0, giving me minus 2. So for the negative signs, we have to complement these and then figure out the magnitude of the complement. So the complement of this is 0, 1, 1, which is 3, minus 3. All right. So go ahead and see if you can form the same table. Write down this binary representation. Remind yourself this is a sign bit, and then practicing if you can come up with these same numbers, where they came from. If you can't, right, remember to ask questions during class, during office hours, on our online discussion forums as well. Right, and here's a set of practice problems. right? So you can practice converting these. So go ahead and practice. You don't know what the right answer is. So if you're not sure about what you're doing, once again, office hours, email, online questions, right? Online discussion forum is really good because it helps you share your learning with other students in the class, and you can all help each other answer these questions. As well as I will go out and read any online discussions as well and answer questions. All right. So how do we convert decimal to ones complement binary? We write the decimal number in its unsigned binary form. If the number of bits are not specified, we use the minimum necessary. We add the positive sign bit as the leftmost bit, right? We have to make sure we have a sign bit. We stop at this stage if the number is positive. If the number is negative, we just complement the entire bit pattern. Okay, let's look at an example. So we want to convert plus 13 in decimal to ones complement binary. So step one, write the decimal number in its unsigned binary form. Right? If I were you, like I said, as I'm following along, I'd be writing this in my notes. You write this down by hand, write these words out of these steps. It takes a little bit of time as you study, but you really begin to learn it this way. Right? It also helps you if you go back later and look at your notes. You'll remember it more quickly if you've written it down yourself by hand. Right? If you just write down the number, you don't know what the steps are. So write the words as well when you study until you really learn how to do this. Okay, so we wrote the number in its unsigned binary form. So 13 is 1101. We only need 4 bits to represent this number. We didn't specify the bits, so we used the minimum necessary. Now we add a positive sign bit on the left. So we had the 1101. Here we put the sign bit right here. We stopped here because the number is positive. So this is the ones complement representation of positive 13. So we converted decimal to binary. All right, now let's convert minus 13 in base 10 decimal to ones complement binary. Same step. We write the decimal number in its unsigned binary form. We use the minimum number of bits because we didn't specify how many bits. We added the positive sign onto the left, right, leftmost bit, but because the number is negative, so the number is negative, we complement the bits of this to form then this. And so this is the ones complement of negative 13. All right, so from decimal to ones complement. Right. Now, let's see how to do it where the number of bits are specified. So we're going to convert positive 13 to ones complement binary 8-bit number. So it's 8-bit binary number. So we're going to write the number in its unsigned decimal form. The number of bits are specified as 8. So if we use 7 bits to represent the magnitude, right, and we know that we can add bits to the left, add 0 bits to the left, doesn't change the value, right? If we were to convert this number from its unsigned form to decimal, we would see that this is still the number 13. We're going to add the positive sign bit on the left to form our 8th bit. Right. So now we have this 8-bit binary number. We stop here because the number is positive. So this is an 8-bit representation of a ones complement number. Right. All right, now let's do the same thing for minus 13. We're going to use, once again, 8 bits to represent it. So we write the decimal number in its unsigned form, right? There's 13. Then the number of bits specified were 8. So we're going to use 7 bits to represent the magnitude. Same thing as before, right? We add these 3 zeros to the left. And then our next step is to add the positive sign bit on the left. We now have an 8-bit number, right? But because we want a negative number, we have to take this number and complement it to form this. So all the zeros here, right, these zeros, these become ones, right? These 2 ones become these 2 zeros. This 0 becomes this 1, right? And this 1 becomes this 0, the 0 here. So this is how we represent minus 13 as an 8-bit binary ones complement number. Right? Now, like I said, you have to practice going through these steps. So try it with some other binary numbers. Try it with any of the numbers that you know 0 through 15 to form that, and actually form a nice table of that. And then try converting it back to decimal for practice. All right, so let's talk about another scheme. This is the 2's complement, the Radix 2's complement scheme. Right? We saw that with 1's complement, we ended up having a +0 and a -0, and that was not what we wanted. So we're going to use the 2's complement scheme. And so our Radix complement is the R's complement. When our base is 2, it'll be the 2's complement. Right? We have a series of formulas that we can use to form the 2's complement number. Right? The 2's complement is basically, or the R's complement is the R's minus 1 complement plus 1. So for the R minus 1 complement, we form that with this formula. Right? For the R complement, we're simply going to add 1 back to that. Right? And once again, we're going to see we don't have to go through in binary this mathematical scheme, that we're going to have a simpler way of doing it. Right? Right. So the Radix complement is the diminished Radix complement plus 1. Right? So in binary, the 2's complement is simply the 1 forming the 1's complement and then adding the number 1 to it. So let's take a look at the 1's complement of -1 is 1, 0. Remember we formed this before by saying that the 1's complement of this number, right, we need at least 2 bits to represent this, a sign bit, so the sign is 1 for negative. It's 0 because we had to complement the 1. Let's go back. We did this once before, but let's go ahead and do it again. So form the 1's complement of -1. All right, so we do that by writing the magnitude of 1, adding a sign bit to the left. Right, so we write the number. Actually, let me kill this. We make this big. All right, we write the number 1 in its unsigned magnitude form, right? Which is just 1. We add the positive sign bit to the left. All right, so we get 0, 1. To form a negative number, complement the bits. So now we have 1, 0. And that's how we get -1. That's how we came up with here that the 1's complement of -1 is 1, 0. Well, the 2's complement of -1 is 1, 1, which is just simply the 1's complement with 1 added to it. So in order to form the 2's complement, we form the 1's complement, and then we add 1 to it. That's all we need to do. So let's see how we can convert positive decimal values to 2's complement binary. We're going to write the decimal number in its unsigned form, same as 1's complement. If the number of bits are not specified, use the minimum necessary. Same thing we've already learned. Add the positive bit as the leftmost sign bit. Same thing as we've already learned. Right? So let's take a look at how we do +13 to 2's complement. Right? We did +13 to 1's complement. Let's see how we do it in 2's. So we write the decimal number in its unsigned binary form. So there's 13, unsigned binary form. The number of bits are not specified, so we only needed to use 4 bits to represent 13. At the next step, we added the positive sign bit on the left. We stop here because the number is positive. Because in 2's complement, we're still going to use a 0 to represent a positive number in the sign bit, and a 1 in the sign bit position to represent a negative number. So if we stop there, that is 2's complement. So what you should write down right now is that sign magnitude, 1's complement, and 2's complement, for positive numbers, they all have the same bit pattern. It's only, the bit patterns only differ for negative numbers, right? So we form positive numbers the same way for sign magnitude, 1's complement, and 2's complement. We do that simply by writing down the decimal number in its unsigned form. If the number of bits are not specified, we just add a 0 sign bit to the left and stop for positive. It's only negative numbers that have special rules. Okay. Here's what we do then for negative decimal values, converting them to 2's complement. We write the decimal number in its unsigned binary form. If the number of bits are not specified, we use the minimum necessary. If the number is not a power of 2, we add the positive sign bit as the leftmost bit. So this differs from 1's complement. If the number is not a power of 2, add the positive sign bit as the leftmost bit. Then we complement the bit pattern and add 1 to the complemented bits. Right, so let's see how we do minus 13 to 2's complement binary. Right. So we write the number in its unsigned binary form, 1101. Number of bits isn't specified, so we use 4 bits. Right. The number is not a power of 2, so we added a positive sign bit to the left. Right. Now the number is negative. Right. The number is negative, so we complement the bits of this. Right, this number, form the 1's complement. So the 1's complement of that is 101010, and then we just add 1 to this number. So this number plus 1 becomes this number, right? 10011, and that is the 2's complement of minus 13. I will give you a table comparing these results in a later slide. All right, but that's how we form the 2's complement number, right? All right, let's work with a power of 2. So we're going to convert minus 8 in decimal to 2's complement binary. So we're going to write the decimal number in its unsigned binary form. So here's how we write 8, right? Unsigned form. If the number of bits are not specified, we use the minimum necessary. So 4 bits are the minimum necessary to represent the number 8. Now, we don't add a sign bit to the left. So do not add a sign bit to the left because the number is negative and it's a power of 2. So we don't change this. But because the number is negative, we complement the bits of this to form 00111. So we complement this to form this. And then when we add 1 to it, we get the same number back. So for negative numbers, powers of 2 are an exception, right? And this is the minimum representation we need to represent negative 8 as a binary 2's complement. Right, so special rules for powers of 2 when the number of bits are not specified. Right, now let's see what we do when we have the number of bits specified. All right, so we want to convert, in this case, plus 8 base 10 to a 2's complement binary 8-bit number. We're going to write the decimal number in its unsigned form. There's our 8. The number of bits is 8 bits. So let's 0 fill to the left to form an 8-bit positive number. Right? So 0 filling this, we have 8 bits. This is the sign bit. The sign bit's a 0, so it's positive. So there's positive 8 in its 8-bit form. Because the number is positive, we're done. We don't do anything else. Remember, we don't complement for positive numbers, only for negative numbers. All right, so this is how we say plus 8 in 2's complement binary, but using an 8-bit representation. All right, now let's convert -8 to 2's complement binary, 8-bit number. So we need to use 8 bits. So same thing again. We form the number 8, right? There's our number 8. But now we need to use 8 bits, so same thing. We're going to 0 fill to the left to form the 8-bit positive number. But because the number is negative, we want to complement these 8 bits to form this 1's complement number. Now, we can add 1 to the complemented bits because this is 1's complement. So now we add 1 to form the 2's complement. So in 2's complement, this is how we would represent the number 8 with 8 bits. All right, so we're going through a lot. You'll want to go back through these slides and practice writing these numbers down. All right, practice forming these numbers without looking at the slides. And then you have the answers here to check to see if you did it right. All right, let's do another number. So we're going to use 2's complement binary to represent -7 with 8 bits. So we're going to write the 8-bit pattern for +7. So here we wrote down 7, and I just 0 filled to the left, right, to form a +7. So that's a positive 8-bit 7. Because this is a negative number, I have to complement the bits. So here I complemented the bits. This is now the 1's complement. When I add 1 to this, I now form the 2's complement. So there's the 2's complement for -7 using 8 bits. It's important that we learn to form numbers with certain bit sizes, right? 8 bits will be a size that we commonly use in hardware. Later, when we learn to form hardware, we'll find that all hardware is fixed in size, and it will give us values that are 8 bits, 16 bits, 32 bits. So we need to know how to interpret whether those values are correctly when we're creating our own hardware, because we're going to create the hardware that does this. All right, that's why we want to start working with fixed bit patterns. All right, now, how do we convert 2's complement binary back to decimal? Well, first thing we do, whenever you're given a number, right, and you're told it's a sign number, look at the sign bit. The sign bit will be the leftmost bit. So if the sign bit is a 1, you need to complement the bits and add 1. Don't change the bits if the sign bit is a 0. So only when it's negative. If the sign bit is a 1, you complement all of the bits and add 1. When the sign bit's 0, do not change them, right? In either case, you now have a bit pattern whose sign bit is a 0. You can convert the magnitude bits to decimal. But if the original sign bit was a negative, don't forget to put a negative sign in front of the decimal number. All right. Well, let's take an example. We want to convert this 2's complement binary number to decimal. So let's look. This number is positive. We don't change the bits if the sign bit is 0. Well, how did I know that number was positive? I looked at the sign bit here. The sign bit is 0. Right? I don't change the bits at all. So now I have a bit pattern whose sign bit is 0, right? And now I convert the magnitude bits. So here are my magnitude bits. Here. So I have 4 bits for magnitude, right? That is the number 13. Because my sign bit was positive, I say that this number was positive 13. All right, now let's convert 2's complement binary to decimal. So I want to look at this number, all right? And I look at it and I say, well, what's the sign bit? Well, the sign bit is a 1. I need to complement the bits. So I take this entire bit pattern and complement it. So now I have 0, 0, 1, 1, 0, 0. I add 1 to the complemented bits to form this pattern. So now I have a pattern whose sign bit is a 0, right? But what I want to form is the magnitude. So I look at this and say, well, the magnitude of that is 13. That's what we did here. But now we have to remember the original sign bit was a 1. So I say that this value, this binary 2's complement here is equivalent to -13 in decimal. All right, that's how we do that. All right, there's an easier way to convert use positional notation, right? There were quite a few steps here. If you're comfortable with these steps, you can follow these steps, but we can use the idea of positional notation, right? Whenever we have a 2's complement binary number and we want to convert it to decimal, right, we treat the leftmost bit, so here, treat the leftmost bit as a negative power of 2. Right. Earlier we showed that positive 13, which was written as this is positive 13. So we had a 5-bit pattern. We had 0, 1, 1, 0, 1. So if we say that these 5 bits, right, these were the magnitude bits. So we have 2 to the 0, 2 to the 1, 2 squared, 2 cubed. And now let's say that the value of this leftmost is negative 2 to the 4th. We can convert this to decimal using positional notation. So if I take this and I say, let's take 0 times 2 to the 4th. So 0 times 2 to the 4th plus 1 times 2 to the 3rd plus 1 times 2 squared plus 0 times 2 to the 1 plus 1 times 2 to the 0. Well, 0 times anything gives me 0. The zeros drop out. So I can just say this is 8 plus 4 plus 1 equals 13. Right? I get the right number. So you can see what we're going to do is when we write out our positional notation, we're always going to put a negative sign in front of the leftmost bit. And we'll end up always getting the right number, and we won't have to worry about complementing. Let's do it now with this bit pattern. So earlier we showed that minus 13 was written as this. Right? Well, once again, let's treat the positions as this is minus 2 to the 4th, 2 cubed, 2 squared, 2 to the 1st, 2 to the 0. Remember we said this was our pattern, so we take this number and say, well, let's convert this to decimal. So we take this 1 and we say this is 1 times 2 to the minus 4th. Remember, the 1 stands for negative sign, right? This will be a negative 8 here. Plus 0 times 2 cubed, plus 0 times 2 squared, plus 1 times 2 to the 1st, plus 1 times 2 to the 0. Well, now this gives me minus 16, plus 0 plus 2 plus 1, minus 13. This, I believe, is the easiest way using positional notation to convert as opposed to all those other steps earlier, right? We had all these other steps where we had to pay attention to whether the sign bit was positive or negative to determine whether we needed to complement and add 1. See, if we use positional notation in this manner with 2's complement, we don't have to worry about whether the sign bit's positive or negative, right? When it's a positive, well, we'll be multiplying by 0, so this negative number will have no effect. When it is negative, right, the sign bit will be a 1. This will take this into account with this position. So this is the method I would learn to convert numbers from 2's complement to decimal. And that way you also don't have to worry about dropping your sign. So this, I believe, is the easiest way to go from binary 2's complement to decimal. And I would work on learning this one. All right, now there's an alternate method for converting numbers, the complement plus 1 step, right? So if you have a positive binary number and you want to convert it to 2's complement, the easiest way to do that for a negative number is to write the number in its positive form. So in this example, we're going to take positive 7 and turn it into negative 7. So we form the positive binary number. In this case, I formed an 8-bit number. So remember our 8-bit version of positive 7? We start at the rightmost bit, and we skip over all zeros until we find a first 1. We complement all the bits to the left of the first bit. So we're going to maintain the first 1. So the first 1 we maintain, it goes here. And then we complement all of these bits to the left. So all of these bits to the left become complemented. And this is an 8-bit representation of minus 7. It's an easier way to form a negative number. Let's actually look at how to do this with minus 13. Let's go back to our 2's complement version of minus 13. All right. Here. So let's see how we do this. Okay, let's get some scratch paper here. All right. Form the 8-bit 2's complement of the decimal number minus 13. All right, so we said one way to do it is we want to write out then, so write the magnitude of 13, right? We did that by saying, well, that's just 1101. All right. Write 13 as a positive A-bit number, right? We did that simply by adding 4 zeros to the left, right? We said form the, all right, 1's complement of the positive 8-bit number, right? So we had to complement these bits. There's our 1's complement. And then we add 1 to the 1's complement to form the 2's complement. So if we add 1 to this, we're going to have 1, 0, 0, 1, 1 as the result. So now, right, we say the so the 2's complement of minus 13 is, well, it is 1, 1, 1, 1, 0, 0, 1, 1. Right. Now, a lot of times when we write binary numbers, we start grouping them in 4s and leaving space in between because it makes it easier for us to read. Okay, so that was one method of doing it. So let's do the same thing here. I'm just going to copy this over here. We're going to form the 8-bit 2's complement of the number minus 13. So we write magnitude of 13 as 1101. It requires 4 bits. So we want to form this into an 8-bit number. Right? 3. To form the 2's complement of the 8-bit number, start with the rightmost bit. Skip over any zeros until you find the first one. Keep the first 1 bit and complement the remaining bits to the left of it. All right, so we have this number. We have this, so the unsigned 13, right, we have this. We have 0, 0, 0, 0, 1, 1, 0, 1. we want to keep this first one here. We're going to complement all the bits to the left of it. So we're going to have 1, 1, 1, 1, 0, 0, 1, 1. Here's the 2's complement. Notice these two are exactly the same. So there were no leading zeros to the right in this example. I kept the first one, there's the first one, and then complemented all the bits to the left of this. Right? So if you want to form a negative 2's complement number, this is an easier method for doing it than forming the 1's complement and adding 1 to it. Choose whichever method makes more sense to you. Right? We remember that the 2's complement is simply the 1's complement plus 1. We'll make use of that later when we create adder hardware in a future lesson. But for now, this is probably the easier way to go from decimal to 2's complement. Remember, we only complement the numbers when they're negative. When they're positive, we do not complement them. All right. So we went back to that slide. We talked about this alternative method. All right, let's look at the 3 methods. All right, so here we have positive values and negative values, right, of n. Here is how they're represented in binary. So these are base 10. Here I'm just showing you what the positive binary integer value is. Right? Here, I'm showing you what the different representations are. So sign magnitude. So sign plus magnitude. So for negative 0, right, this is sign plus magnitude. This is -1, -2, -3, 4, 5, 6, 7. So here is how we represent this with sign plus magnitude form. Using 4 bits, so we're using 4 bits here, we cannot represent the number -8 with sign magnitude. With 2's complement, we don't have a -0 in 2's complement. There is no -0, so that's why we show that as not being representative. But we have a -1 through a -8 because we have the special rules for powers of 2. In 1's complement, this is -0, right? And this is -7. So here's your 1's complement representation. Notice with 4 bits, once again, 1's complement, we can't represent -8. So notice the positive integers are the same for all 3 schemes. Sign magnitude, 2's complement, 1's complement. All we do is we write down the magnitude. So here's the magnitude of 0, and the sign is 0. Notice that each one of these, the sign bit is a 0. So whenever we have a positive number, we just always write down the sign bit plus the magnitude. We do that for sign magnitude scheme, 1's complement scheme, 2's complement scheme. Positive numbers look the same in all of them. Negative numbers you can see differ, right? In this case, let's look at -1. Sign magnitude, here's how we represent -1. 2's complement, here's how we represent -1. 1's complement, here's how we represent -1. All right, 3 different schemes. All right, we need to know what's good and bad about these schemes, which is why we took a look at the value of how these are formed. We said these 2 schemes are not good in that they have a representation for both +0 and -0. The best scheme is 2's complement. So almost every computer uses, or programming software uses, a 2's complement system when they interpret numbers, right? So that's what we'll be using later when we form hardware, simply because for 4 bits we can represent a greater range of numbers, right? So let's take a look at this question. What is the decimal value of this binary string? Well, we don't know unless we're told how it was formed, right? This could be, if this is an unsigned number, Is it a signed number? And if it is a signed number, is this signed magnitude? Is this 1's complement? Is this 2's complement? So we must know whether this is a signed or an unsigned number. If signed, we just said it could be one of 3 schemes. So let's take a look at this number. If it's a signed 2's complement number, well, we could convert it back to decimal by using this idea of positional notation, where we said let's treat the leftmost bit as a negative power of 2. So negative 2 to the minus 7th is 128. So 1 times negative 2 to the minus 7th gives us negative 128. Well, all these zeros give us 0. We could add in 1 times 2 squared. That's where the 4 comes from. And then 1 plus 2 to the 0. And so if this were a 2's complement number, we'd say its decimal value is negative 123. But if it's an unsigned number, right, if we're told this string is unsigned, then there is no sign bit. All we do is we take this and we convert it to decimal. So we use this positional notation to convert binary to decimal, and we say this is 1 times 2 to the 7th plus 1 times 2 to the squared plus 1 times 2 to the 0. Or 128 plus 4 plus 1 equals 133. So it's important that we know how this number was encoded before we can give it meaning, right? Meaning to us is normally a base 10 number system. Right? If we were to go on then and finish this and say, so this is the same binary string, but now if it were 1's complement, well, in 1's complement, we know that 2's complement is simply 1's complement plus 1. We could use this positional notation to form the value of minus 123, add 1 to it and say it's minus 122. Or the other thing we can do is, because this was signed 1's complement and it has a negative sign, in order to get the decimal value, we could complement it back. So we could form the complement, right? We now have a positive value, so we find the magnitude of this number. The magnitude of this number is 122. What we remember is that the original sign was a minus sign, so we put a minus sign in front of this calculation to get minus 122. Right, so 1's complement, remember, is 2's complement. I'm sorry, 2's complement is 1's complement plus 1. So 1's complement is 2's complement minus 1, or minus 1, a negative 1. Right, minus 122. And then if this number were signed magnitude, well, in signed magnitude, all we do is we look at the sign and say, okay, this is a negative number. And then we find the magnitude. So the magnitude of this number is 5. So we'd say this number is minus 5 in signed magnitude. So as I said, it's very important that if you're asked to convert a number from binary to decimal, you have to know how the number was encoded. All right, we're about to the end of our topics now. Let's talk about number ranges. Right, number ranges are based on hardware size or the number of bits. We're always concerned of how many unique numbers we can represent with the number of bits, right? Unique numbers represent unique information. Computers store information. We need it to be unique. Right? So physical hardware components have a fixed number of bits. Right? Decimal 15 in binary is a string of 4 ones. This requires a minimum of 4 bits to represent this number. So if we had hardware that was limited to represent 3 bits, we could not represent the number 15, right? The largest unsigned decimal number we can represent with 3 bits is the number 7. Remember, 2 cubed is 8, so we can only represent 8 unique values that range from 0 to 7 in unsigned. Right? So let's take a look at the range of unsigned decimal numbers. Right? In a decimal system, we know that with integers, so 0 through 9 we represent with 1 digit. 0 through 99 takes 2 digits. 0 through 999 takes 3 digits, right? And 0 through 10 to the n minus 1 with n digits. Right? So in this case, if n is 1, 10 to the 1 minus 1 is 9. Right? If in the case where n is 2, right, 10 squared, 10 to the second power is 100. 100 minus 1 is 99, 0 to 99. Right? When our digits are 3, 10 cubed is 1,000. 1,000 minus 1 is 999. So 0 through 999 with 3 digits. Right? Same way, if we had 4, we could represent the numbers 0 through 9,999, because 10 to the fourth is 10,000. Right. So let's equate this then, same formula, range of unsigned binary numbers. So unsigned binary numbers are represented with a range. Here's the formula: 0 to 2 to the n, where n is the number of bits, minus 1, inclusive. So meaning we can represent both endpoints. So let's say, what happens when n is 4? When we have 4 bits, what range of unsigned numbers can we represent? We can represent 2 to the fourth is 16 minus 1, of the range of 0 to 15, which we wrote out in another lesson, the binary pattern 0 to 15, and we know it requires 4 bits to represent the number 15. All right, so the number of bits determines how many unique quantities we can represent. Right. Now the range of signed magnitude numbers, right, we have to be concerned with ranges of negative numbers and ranges of positive numbers. Remember, the leftmost bit is the signed bit. The remaining bits that we have are used to represent magnitude. So basically, we're splitting those binary patterns in half. Half of those patterns represent negative numbers, half represent positive numbers. So we're going to have this range. And this range, in general, for n bits, the range of signed magnitude numbers is minus 2 to the n minus 1 to positive 1, right? Plus 1 to 2 to the n minus 1 minus 1. So this formula, this is the negative range. This is the positive range. Remember, sign magnitude has both a plus 0 and a minus 0. So let's take a look at an example using this formula. Let's say we have a 3-bit number. In other words, little n is equal to 3. But we've got 2 bits to use for the magnitude. So we can represent 4 unique combinations of the magnitude. 2 squared is 0 to 3, right? So 2 minus 2, so when we've got 3 minus 1, here, let me just say. So minus 2, and actually, n is 3, so let me use the font here to say, okay, so we've got, okay, 3 minus 1, and now I've got to turn that font off, write this out, plus 1, plus 1, 2, I'm just going to put this into the formula here. This is plus, minus, right? Well, that's going to be equal to minus 2 squared sorry, where's my font? Squared plus 1. Put my font off. It would probably be faster if I did this in a formula. Plus 1, 2, 2. Squared minus 1, which happens to be equal to, well, this is minus 4 plus 1, so this is minus 3, 2, and this is 4 minus 1 plus 3. So minus 3 to plus 3. And that was found by plugging that into this formula. Okay, so that's how we got that range of sign magnitude. Now, here's the formula you use for range of one's complement. It is the same formula, right? If we go back to this table, back to this table, Here, sign, magnitude, and one's complement can both represent the same range of positive and negative numbers, right? Just a different way of encoding them. So they have the same formula to represent. So for 3 bits, you can still represent -3 to +3. Right, remember we have a +0 and a -0 in each one of those. Finally, 2's complement. Here's the one we're more concerned with. How do we represent a range of numbers in 2's complement? Once again, half of the table is for positive numbers, half is for negative numbers. So when we have 3 bits, we still have 8 unique combinations. Half of those combinations will be negative, half will be positive. But here's your formula. So in general, for n bits, it's -2 to the n minus 1 to 2 to the n minus 1 minus 1. Right? So if we let n be equal 3 bits, our range is -2 squared to positive to 2 squared minus 1, or -4 to +3. Because with 2's complement, on the negative side, remember we have that special rule for powers of 2. So we can represent one more negative number with the same number of bits using 2's complement than we can with 1's complement or sign magnitude, right? Remember with 2's complement, we don't have both the plus and the -0. We just have plain old 0. So that leaves us room to represent one more negative number. All right, so you want to know this formula for range of numbers. All right, if you can't remember the formulas, you should always be able to puzzle it out based on your knowledge of how to form these numbers. Okay, so we're going to stop here with this part of the lecture. We've been through quite a bit of material. We'll come back. In the next video, we will talk about sign binary addition.